Hold everybody else.
All right, we're gonna get started here. I'm extremely pleased to introduce my friend Dr. John Hood. He's at University of Chicago. He works with almost all the various collaborations at the South Pole. When I was there, he was doing some experimental instrumentation stuff, but now he's gone to the dark side of just doing observational things with AGN. But we still let him come here and give the talk. So over here.
Oh man. Thanks for the introduction, Alex. Thank y'all for having me too. So my talk it is mostly about some observational work, but it's towards the end. I'm gonna be peppering in like a couple of other like projects and things that I've been working on that I'm like it's kind of like proud to talk about, like discuss a little bit of education and outreach things that I kind of like dabble in on the side when I'm not stuck in the lab or in the office, like working on AGN stuff. So SPT stands for the South Pole Telescope, which is a cosmic microwave background experiment originally built to observe the cosmic microwave background in 2007. Since then, there have been 3 different instruments installed on this telescope. Niels could probably tell you a lot more about like some of the backgrounds of the earlier ones than I can. But from 2007 to 2011, roughly, it was called the SPT-SZ instrument. From 2012 to 2016, it was the SPTpol camera or instrument. And then from 2017 until present, it was the SPT3G. A lot of the data, well, all of the data that I'm going to be talking about, like for the rest of this talk, was generated from the SPTpol camera. So that 4 years of observations is kind of like the central focus of like the work that I've been doing. 3rd generation. Yeah. So as astronomers, like kind of horrible with naming things, you just kind of call it what it is. The current iteration that we're working on is SPT4, just the 4th, this is 4th generation. They didn't want to put the G on it.
Following the various naming conventions.
Exactly. Exactly. So the SPTpol camera, one of their main focuses was this 500 square degree survey, which is again where all of the data that I'm going to be talking about came from. The laser doesn't really work on the TV screen, so I'll like walk over and point and stuff. This camera during its time was able to observe not only in intensity, but in polarization. The polarization is a bit tricky for the stuff that I'm working on, which I could talk about later. I already discussed with some of y'all in the room. But what I wanted to do in my research was take CMB observations and use them for not CMB things, because I was never really a CMB person. I came from a very observational astronomy background. So these observations were taken in both 90 gigahertz and 150 gigahertz to cover this entire survey field, with over 9,000 hours of observations over these 4 years of time. So like I said, I wanted to repurpose this. So what I did was took the CMB observations, and what they would do is they would mask out all of the bright point sources because they were just background noise and got in the way of studying that. I wanted to do the exact opposite. So what I did was I built what's called a match filter, and I filtered out the CMB instead of the point sources, which is where I went from this map on the top here to the map on the bottom. To kind of give you a zoom in on what that looks like, to show you an even more clear view, is this square patch that's highlighted now shows there's a AGN hidden in this field, which you'll see this image kind of floating through the rest of the presentation. But you can see that there are a number of bright sources, but there's also just like a lot of like long wavelength variability of like this kind of like waving like blotchy patches in the image. Once I applied the match filter, I was able to remove all of that, which made the brighter point sources stand out a lot more, with some of the other point sources still being able to kind of like stand out within that field. So we can actually do science with those things instead of them just kind of being tossed aside and not being used. So this is an example of like what one of these bright sources look like. And this is actually one of my favorite AGN in the field, because what happened here, we still don't know. It was very interesting. We're trying to figure out what was going on. So if you watch along with this line, as well as this image, if you have a keen eye, you might be able to figure out which one of these sources is the AGN that we built this light curve from. If you can't, I'll tell you now, it's this one right here. And the way that you can kind of tell that is you can see like when this source is brighter here, you can see that the darker ring, which is a which is an artifact of the filtering process. The brighter the object gets, the darker the ring around it would get in individual observation. So when this source is extremely bright, that ring is a little bit darker, showing that the source is brighter. But when the source gets dim, you see it just kind of like fading into the background. Alex.
What's the scale on the time down here?
So the time is in labeled here. Thank you for that. Is in modified Julian dates, but this is just over the 4 years of time. So this is starting in around 2000, late 2011, early 2012, up until like 2016. And then the flux over here is in millijanskis, units of millijanski. So question that you might be wondering is like, why do we want to study AGN in the millimeter? Which again, like some of us have already talked about this earlier. We want to understand like, do the physical mechanisms that cause gamma ray and optical emissions also produce millimeter wave emissions? Like how connected are those? So we want to do correlation studies to understand that. And mostly because we are looking here in the synchrotron peak. And some of the unified model of AGN says that if you observe a flare in optical, you observe one in the gamma rays as well. And since we know that the optical emission is from synchrotron emissions, and millimeter is a strong tracer of synchrotron emissions, what we were hoping to see was a strong correlation between the optical and the millimeter so that we can say, okay, the models such as the leptonic and hadronic models, or mainly the leptonic, that say that if you see one flare and one, you see it in the other due to synchrotron self-Compton scattering, we can kind of prove that and give it an additional like level of validity with our study. And again, we wanted to see like, are there correlations between optical and gamma rays or millimeter and gamma rays, or how can we trace that with our current data set? We initially did this by doing a pilot study of a source called PKS 2326-502. I will not say that whole number for the rest of the time, so I'll just say 502 if we need to. Fun thing about that is that's the exact same light curve that I just showed y'all earlier. So like I said, you're going to see that quite a bit during this talk. So during this pilot study, we used observations from 3 different observatories. The South Pole Telescope, which we only used the 150 gigahertz data for the purposes of the pilot study. For our optical data, we got our data from the R-band instrument, the R-band from the CTIO SMART Observatory in Chile. And for the gamma rays, of course, we got those from the Fermi Gamma Ray Space Telescope. The way that we found our sources was we had to cross-match against all 3 of these different catalogs. So the circles here, the yellow circles indicate all of the Fermi for FGL, the Fermi monitor source list of AGN that we looked there. The red circles, there's only 2 of them, is from the SMARTS catalog. The reason that there's only 2 of them is because being that this field is from the South Pole, the majority of the sky is above Antarctica, with only the top strip really being visible from a lot of observatories in like parts of Chile. The blue sources, the blue circles, are sources that we cross-matched between this SPT catalog and the AT20G catalog. The reason that we did that cross-matching is because we wanted to make sure as much as possible beforehand that a lot of the sources that we were looking at were bright AGN instead of other possibly like dusty galaxies and things like that. And on this, you'll notice that there's only 2 sources that are highlighted. And if you remember from where that square was earlier, this is our source 502. This source over here, while it did have data in all 3 surveys, the SMARTS data set, the light curve that they had, I don't really want to call it a light curve because it only had like 10 points spread out across like 8 years of observations. And it was like, we can't really do much with that for what we were trying to do as far as like correlating light curves and activities. And so we kind of just went with the one that we had the most data for. And this is what all 3 of those light curves look like. So from top to bottom, we have our Fermi data, our optical R-band data from SMARTS, and at the bottom here is our millimeter wavelength data from SPT at the 150 gigahertz band. So there's 3 squares here that we really wanted to focus on in this study. So between the millimeter and the gamma rays, we can kind of by eye see that in this first year, there is this really long time scale increase in flux. So we know that that's going to be correlated just by eye between those 2 bands, or we felt it was safe to assume that those would be correlated in long time scales. But once we actually flatten out the optical flux, we noticed that there was a flare in the optical and seemingly a flare in the gamma rays as well, which is the kind of magenta, square, or rectangle that's highlighted here. So in order to try to understand these like a bit more, we had to try to massage the data a little bit to try to see what we can actually get out of it. And what we did there in order to do that was we applied a certain level of like filtering and smoothing to the data to try to see what things would look like with from a different point of view. So compared to the first set, the first column here is where we apply what's called a boxcar smoothing to the data, which really just kind of like hammered down like a lot of the fine wiggling and wobbling of the data and made the lines a lot smoother. The next thing, and in this, so from top to bottom, we have SPT cross Fermi, SPT cross smarts, and then Fermi cross smarts, or other words, it's millimeter versus gamma, optical versus millimeter, and then optical versus gamma rays. In the second column here, what we have is the same boxcar smooth data set, but we also detrended it. And what I mean by detrended is we actually subtracted about a third to fifth order polynomial to flatten the light curves down to where all of the long time scale features were dampened and all of the short time scale features were amplified. And each of these blocks here, and these 6 on the next 2 plots, is going to be the 1 year worth of data. This is the first year. So this is like, again, modified Julian dates, and then like the flux on the y-axis. So just looking at these, you can see there's nothing between SPT and Fermi, nothing really between SPT and smarts. And if for smarts and Fermi, we can see that there's still this correlated peak where that flare happened. And then to kind of quantify that even more, we did do a cross correlation function for the detrended data. And again, we can see there's really no correlations. Trust me, that blocks in the way, but there's no peak at 0 or anything there for the top block. There's nothing there, but then we get a very significant measurement for correlation between optical and gamma rays at this point in the first year, which is where we see this like very short time scale light curve or short time scale flare going off. We did the same thing for the second year, and this is where we kind of got some surprise results, where doing the same thing for the second year, you might have noticed there was like a little bit of a bump as that light curve is going down. You can't really see it now because the block up there for Zoom is in the way, but we measured a somewhat significant measurement of the correlation between SPT and Fermi within the second year of our light curve. So this told us that while on certain timescales we might not see anything, on the others we might, which on some of the shorter timescales we also see correlation between SPT and Fermi. So to do a quantitative result of this, we had a PhD student. He was an undergrad REU student at the time. He's now a PhD student at UChicago. Aiden Simpson helped us develop a 0 lag correlation function. And these are the results of that, where, again, the table basically just shows what I was just saying. We measured a significant correlation between the optical and gamma rays for the first year, and a somewhat significant correlation between the millimeter and the gamma rays in the second year. So we did a 0 lag correlation, and the p-value for that, along with for the smooth and detrended data for the first 2 years alone. The reason that we didn't do this for the second 2 years is we had gamma ray data and millimeter wavelength data, but if you remember the light curve, there was only like 1 point per 2 years for the smarts data for that same source. So with the findings that we came with from that was we found that there are some long time scale correlations with Fermi and SPT, which we saw those by eye, which we immediately kind of like excluded those in like the further analysis because we wanted to see if there was anything deeper that we just couldn't see. We found short time scale correlations with Fermi and smarts, which were during that first year where the correlation was like very significant, like measured in that previous plot, which, sorry, one thing that I didn't say, and I'll take a step back to say this, just in case you were wondering, I did not say this. The gray envelopes here represent the 1, 2, and 3 sigma correlation errors or significance of that. So outside of that, where this one has a peak above that, that's why we know that that's a very significant measurement. Sorry that I missed that the first time. We also found that there were some short timescale correlations with Fermi and SPT. We believe that was in the second year where we had a small bump in the light curve as the flux was starting to fall. It started to rise again. We saw that in both of those light curves. And we found no measurable correlations between SPT and smarts, which was the most surprising result that we had, being that we went in assuming that that was going to be our strongest like factor going going into this. So what we believe this tells us after the fact is that this lends support to the synchrotron self-Compton model of gamma ray synchrotron photons and blazars being the more prominent model, because we did find evidence pointing towards that being what's true. But it also implies that the synchrotron photons responsible for the millimeter wave emissions in this source are produced separately from photons responsible from optical emissions, which kind of goes into the conversation that a couple of us were having previously, where we're trying to figure out some of the theoretical things that might be causing this, which made me really happy, because like more normally people are still just as confused as we are, and we're trying to figure out like what might be the problem here. So the next step that we took after that to try to make sure that we knew more and we could try to find out more about how these things work was we started the development of an online catalog and producing Lightcurves for all of the sources that we had in the field. So I showed before where there were a number, about 158 different AGN within that 500 square degree survey that we could produce like high signal to noise Lightcurves for. And in doing that, we can do a similar analysis for all of those. So the development of this came about, and we also decided to start exploring the polarization of each of these objects as well, because by understanding both the flux and the polarization, that opens up a lot of doors in the millimeter for us to try to understand like different aspects of what's going on within these frequencies. I additionally joined, as Alex and Nils pointed out, almost all of the other CMB collaborations out there, because this project was actually going so well that they felt that it was a good thing to have going in all of the different data sets. So not only have I been able to get a pipeline running for this with the South Pole Telescope Group, I've done the same thing with the Atacama Cosmology Telescope, or ACT, Simons Observatory, and Simons Observatory as well as like helping some of the preliminary work for getting things done like this for a project called CMBS4, which is kind of like ongoing and being on development for opening up in the future. The website that I built for this, the catalog, is public facing. I'll talk a little bit about more of that in a second. And in the future, we want to try to combine these observations with observatories like LSST and VRO to try to get more similar cadence data, so that we don't have a similar problem what we did here, where in the last 2 years there was no data, or in the first example there were 2 sources and one of them only had like 10 points for 4 years. So in doing this, we're kind of hoping that other people will see this and see the importance of monitoring AGN on a high cadence, so that we can do more cross correlation data like this with multi-wavelengths. And this kind of guy goes into like building the catalog and why. So we started this millimeter wavelength AGN monitoring system, and I call this like the intro to building the straw hat catalog and beyond. So on this image here, I show the SPTSZ field, which is where we got a lot of the names and identifications of our point sources from. The SPTpol field is the green dashed line, which is where all of this is the 500 square degree field that I've been talking about mostly for this presentation. And then the SPT3G field, which is a 2,500 square degree field as well now, because it expanded from the 1,500 square degree field that it previously was. And all of these sources within this orange footprint in particular are going to be updated and added to our online catalog in the future. Along with that, I'm not sure if they will be added to the Straw Hat catalog specifically, because part of the name for Straw Hat, the acronym is SPT, so I might have to rename it or something along those lines. But this is the survey footprint for the ACT telescope, which is the majority of the southern hemisphere sky. And this is the footprint for what the Simons Observatory would be able to do, which is actually 70% of the southern hemisphere, or 70% of the sky. And the development of this, is the launching of these different programs, has enabled us to actually, within ACT, currently, we have the Lightcurves of roughly 200 bright AGN that we're working on, like trying to do different types of analysis for. And we're adding these to an online catalog and like repo for people to use those as well. But for Simons Observatory, which actually just got first light last week, for those who aren't aware. So we're really excited about that. Only one of the telescopes is online, but we're hoping to have like another 6 or 7 online by the end of the year, being able to observe the majority of this footprint. So once we have that, we're expecting to go from roughly 200 to around 1,000 different AGN that will be able to produce these high cadence, like every 36-hour Lightcurves for. So now to tell you about the Straw Hat catalog, which stands for the SPT Treasury Record of AGN with Historical Activity and Time Series. It is a very long acronym, but I love the show One Piece, and I wanted to do whatever I could to have a catalog named after something dealing with the show. But as I was saying before, like this is currently what the website looks like right now. It only has 150 gigahertz data uploaded to it. We have all of the 90 gigahertz data ready. It just needs to be put up on the website with the plots and everything for people to download. But to kind of give you an example, right now I said it only enclosed the 150, but it will have the 90 as well. And in the future, once we have more confidence in our polarization data, the polarization data will also be included for all of these sources. In addition to that, within the next 2 years or so, we're planning on also including all of the 90, 150, and 220 gigahertz flux light curves for a few hundred additional AGN from that 2,500 square degree footprint from the SPT3G survey. And I say this is an attempt at an all most of the sky AGN catalog, including data from SO, ACT, and CNBS4. We will see how that goes. As you can imagine, trying to do joint collaboration projects like this can be a bit tricky due to internal politics and stuff, but it seems like everybody's mostly on board. So if it's a separate catalog, I'll name a different one. But for right now, this is what we have. And this is kind of the logo that a friend of mine might help me come up with, which is Luffy's hat, basically, from the show One Piece. So like near future and outreach projects that I've been working on that I was saying, like I kind of want to talk about a little bit. In the near future, one of the problems that I mentioned is having very little optical data to go with what we want to do as similar cadence. So this is the current footprint of Simon's Observatory. Actually, this is kind of outdated now because there's an old telescope over here somewhere. But this is the area where Simon's Observatory is currently sitting. Working with that collaboration, I'm actually working on building an optical telescope there so that we can have our own in-house optical observations to do transient follow-ups as well as AGN monitoring on whatever cadence we so choose to, instead of kind of depending on writing proposals to get time on somebody else's telescope. It'd be better if we had our own like in-house optical observations to go with that. What I plan on doing is doing like optical, possibly near infrared monitoring with a 1 meter class plane wave telescope that we're going to build either on the grounds at Simon's Observatory or at the Parque de Astronomica in Chile, which is very close by and all run like solar powered, so that we don't have like too much of like electronic footprint. We don't want to have to carry more diesel up a mountain just to run a telescope. So I figured I'm going to try to do everything that I can to prevent stuff like that from happening. The tricky part about this is we were working to submit the proposal later this year, which given the current climate with NSF, we're not even sure if that's going to be around for us to apply to. So if so, then this is what we're going to be like aiming for to do later this year. It was actually nice. James was able to take me to the observatory earlier today, which made me feel really good because it's like similar camera and filter wheel setups out there is what we plan on implementing in the at this observatory in Chile. So this is kind of like this is my solution to where's the rest of the optical? How come we can't do optical for all of the years the same time scale? This is our solution to that problem. And an education and outreach program that I'm very proud of is a program called Rizzo and Rio. It stands for Real-Time Interactive Solar Observatory and Real-Time Interactive Observatory. Basically, what Rizzo and Rio allows us to do is it allows students in like more rural and like remote areas, as long as they have internet, they can sign in and control one of our telescopes remotely. They can do solar observations during the day, or if they choose to have a program at night for like even like undergrads or like high school students to do research projects with, they can sign in at night. The way the program typically works is we have one student there and an observatory technician in the observatory. The current observatory that we're running this out of is the Meade West Vaco Observatory in Columbus, Georgia. It's connected to the Coca-Cola Space Science Center and Columbus State University, which is where I did my undergrad. The reason that I'm like so proud of this program because I was actually a part of this, like the initial development of this program back in 2013, 2014. I've been working with them this entire time. We write lesson plans for different like age groups. We go everything from kindergarten up to 9th, 10th grade. Uh, so yeah, we go do kindergarten up to like high school, like 9th or 10th grade. A lot of the students who work on this they work primarily through the Georgia Space Grant. That's how they kind of like get their funding to like do projects like this and everything. We also work in the process of working on the development of a planetarium show that's going to be about the transient universe, where we're going to be talking about how you can use things like this and different people that are involved with transient studies. They were doing different things like in that show as well. The images down here, I have to mention, this one is honestly like my favorite. It was like astronomy picture of the day, like years ago when we first did this. It was a second grade class, one of our first groups that actually got involved with this. You can't really see it from like far away because it's like a little pixelated like on the screen, but this solar flare just happened to go off while the second grade class was observing, and the kids completely lost their minds. And they were so excited. And all you hear from it was like they planned it. You just hear a bunch of second graders yelling, "It's a dragon on the sun!" And we're like, everybody's looking like, "Oh, it kind of does look like a dragon." So they actually named it after their teacher, and they submitted this to APOD and actually won APOD. So it was forever known as Getz's Dragon, is the solar flare. And just moments like that is like really kind of like what makes me happy about like doing what I do and like being able to do things like this, like reach out to like people who may not feel like they can do this type of stuff, or maybe they have an interest in it, but they don't know really how to get involved. Programs like this is like kind of helping young minds find ways to develop that interest and like find it at its peak and like push them along the way to do that even more. And then the other one is just the first image that we took during the night observations of the Orion Nebula, which it was another thing. It was like some of the first images, some of the first things that we did with this program. We are also currently looking for people to partner with us to expand outside of Georgia as well. So we're looking for different like planetariums and institutions to get involved with like having like remote access, because as you can imagine, if it's cloudy in Georgia, you can't really like turn the telescope on and look at anything. So it'd be a good thing for us to be able to like have other institutions like, okay, it's cloudy there. There's an observatory, like say, for example, the observatory here's like the observatory in Colorado is like perfectly clear. Let's just patch them in instead. And we can do the same thing, like have lessons run that way. So, and that would be the end of my talk. I'll go back to this one just because the pictures are really cool. But, but thank you for having me. Questions? Thanks.
Yeah, I have a question, but I also want to say this is really neat. This is really cool. But my question is about you had the figure out of all the events identified by the different telescopes, like different color circles, basically. I was curious about like a lot of these. So there's two overlapping ones, but then a lot of these don't overlap or overlap just two of the colors. Like, what are those events? What are those?
So the yellow ones are like known like Fermi sources. The blue ones are like sources that are SPT, that are basically like cross between SPT and AT20. There was a study that was done around the same time where, for example, these that don't have any overlap with SPT. There was a catalog that was done by Li Zhang Wei, I believe is his name. I can't remember his name right now, but he basically did an analysis showing that there were a number of sources that SPT had missed in their catalog that were marked in Fermi, and vice versa. There were also some SPT for sources that Fermi didn't see, but of course Fermi doesn't see all of these because they pick up things that like emit like gamma rays at some point. They have to have some kind of gamma ray flux coming from them. So that's why you don't see like full like matching for all of these. Thanks. No problem.
When the polarization stuff is ready, what would you expect to see? This like, will it just be like joggled, or like can it go through like, I don't know, like a low intensity feeling? You can see like Faraday rotation and like, you know what I mean?
So the big thing that we're looking for is we've been working with a collaborator from Stanford named Greg Majinsky. He was telling us about a study that was done in the optical, where they noticed, or in optical and radio, I believe, where they noticed that whenever a flare happened, the polarization angle of the jet flips.
Yeah.
So we're hoping that we can see something similar in the millimeter, just to kind of like help verify that that's actually like a thing that happens. There are a couple other like random ideas that people have of like how the polarization can like help us understand different things, but that's the only one that's kind of like really stuck for a long period of time for us to try to focus on looking at. So like if you have any ideas of what we can think to see from that, like I'm more than happy to like listen and like take that down, because Yeah, like I said, the only one that's stuck is the polarization angle flipping. Yes, you can. So it's really about having, as long as you're in a location where you can get like enough sun, it's all about like the storage banks. Because if you can track how much power the telescope needs during observations, like during idle time and during like actually like tracking, it's kind of easy to convert that to how much power do you need stored to just have it running off the batteries. Because the solar panels will just be collecting power the whole time regardless. The tricky thing is getting the telescope operating, the computer running it operating the whole time, and the power to keep everything else running. Because in the area that it's at, like we were told that we would need like security cameras, maybe some like small like lights to go in there for when people are there like working on things, which if done properly, the way that I have it planned as of right now, we won't need to have anybody there more than once a month, maybe, just to do like preventative maintenance. Like one of my goals in like having this like remotely operated telescope was to have it as a remotely operated telescope with as little of a footprint as possible. Like all we have to do is just turn it on, let it do its thing, download the data, and then just turn it off in the morning. Like as long as we're able to keep that up, then it shouldn't be like too much of a power draw. One thing that you also might be thinking about is like temperature, keeping like the temperature stable inside of the enclosure of everything where the dome is and where the people might sit. We don't have to worry about having a heater in there if there's no people in there, because as long as it's not so cold that the computers just drain battery, we don't have to worry about that. And in Chile, we don't have to worry about temperatures that cold. So that's kind of like my general plan of like having like a completely solar powered right now. There's still like some small details that we need to like hammer out, as far as like the big one right now is like the computer. Like if the computer is always on, which it will have to be in order for us to be able to like remote in, like turn stuff on and off, we need to figure out like how much power is that going to draw like on a daily basis. And I figure as long as like nobody downloads Steam to it, it shouldn't be like too much power like on a given day. So
So I know that, eventually the sun comes up in the South Pole and,
Mhm.
you have those gaps in your observations there. But you had a pretty decent correlation between your millimeter data and your gamma ray data. So that gap with like exponential increase, gap, exponential decay out the other side, it took me a second to be like, oh wait, they don't have data in that time, not like the data went off the charts.
Yeah.
In that time.
That's
So
very
what's your
frustrating.
best guess? Does it go off the charts? Is there a dip in the middle? Because we kind of see like another dip on the other thing. Does it just curve out? Like
How much time do we have left? Because like not argued, but we've had very many discussions about how we could possibly interpolate what happened right there. And it's like, we could, but then the interpolation, we have to tell it if it increases or decreases. So it's like, we just don't know. Yeah, like, we were also all in agreement that we didn't want to do that, because it would degrade like the mystery behind it. Like we were honestly hoping that we could possibly get data from like one of the other telescopes to try to get something similar, but I believe ACT wasn't turned on at this point, and there was no other like millimeter observations like happening with this source at the same time. So it was very disappointing. I was very sad. I was like, come on, man, nobody was looking at this. But it is extremely bright. It was a very bright flare for over a year. And it's one of those things where I've also come into an understanding of, a lot of people see AGN as transients, but not transients. So it's like transients are things that go boom and then go away. This is going like instead of just like an immediate brightening and then going away. So people probably observe this a couple times within this time frame. They're just like, oh, it's just varying. It's just bouncing around like a little bit every couple days, and they come back like 3 months later. It's like, it's a little bit brighter, but it's just not doing anything amazing. So yeah, there are some that we have where we've actually caught them within 1 year where the flux would increase by a factor of 2, dip by a factor of 1, and then increase back to where it was originally at that factor of 2 increase, and then drop back down again. Like we've seen some weird stuff with these light curves, and there's a lot of questions to ask, like what's going on with that? Like what would cause that to happen? Which is really why I like chasing this down, because there's like so many weird things. I like to call it's like monitoring AGN is like astrophysical people watching. Because like they all have their own like personalities and they all do weird stuff, and it's just interesting to watch them and see what they do over time.
Thanks, Jonathan, for an awesome talk. John will be here through the afternoon, and the schedule you should all have it if you wanna, figure something out.